I'm going to talk about some intermolecular forces here in this video. These are forces that are between molecules, or it can be some atoms. We'll talk about that exception here, but between molecules in general. So, first of all, between molecules in liquids and solids, there are some intermolecular forces that happen in gases, but they're very, very weak. Officially, there are some, but this is really explaining how substances stay together as liquids or solids. So they're not bonds. So intermolecular means between two molecules. Intramolecular be within that molecule, just like interpersonal communication is from one person to another person. Intrapersonal communication is kind of the dialogue you have with yourself every day. So for this, we're talking about what's keeping the molecules held together. They do vary in strength wildly, but they're definitely much weaker than an ionic or covalent or even a metallic bond. There's four different types that we're going to talk about. Dispersion or a London force. Some people call them a London dispersion force, which is the weakest, as you can see on this list. Dipole-dipole, which is a little stronger. Hydrogen bond, which is annoying that they call it a bond. But it is called a hydrogen bond, even though it's a type of a force. Forces are generally between molecules, bonds between two different atoms. And then there's an ion dipole force, which would be not just between molecules, but between an ion and a molecule. So before we do this, we're going to do a quick little review of polar and nonpolar molecules, because we need to know the difference between them to be able to figure out what types of forces these molecules are going to have. So first of all, the typical polar molecules, if we remember from our past, generally bent, trigonal pyramidal, and as we talked about in past chapters, linear kind of can fall in between because it depends so much what type of a molecule you have there, because you could have H with H, no different electronegativity, or you could have like H with F. There's a big difference electronegativity there, so it makes it polar because our dipole would point to the right. We'd have a partial negative charge here, a partial positive charge here. Those partial negatives and positives are what are going to be involved in these forces of attraction. And then the nonpolar are really the rest, so the very symmetrical molecules, and I'm not going to write them all out right now. But the examples would be, or all the molecules would be trigonal planar, tetrahedral, octahedral, trigonal bipyramidal. All of those would be included in nonpolar molecules. So some examples: water is polar because it's bent. Ammonia is polar because it is trigonal pyramidal. Nonpolar things, something like methane, or what else is carbon dioxide, very common molecule because it's linear, but the dipoles cancel out. So it's a little review from our past, because to be able to identify the types of forces that exist, we need to be able to remember or know what types of molecules we're talking about. So the dispersion or the London force is the weakest. It exists among the nonpolar molecules, as you see there, and noble gases. So anything that's nonpolar, or if it's a noble gas. So it's kind of weird that as far as we're talking about any type of a noble gas like neon or argon, how could they ever form a liquid or a solid? That would be by having these types of forces together. So they're short-lived, very weak. Temporary dipoles affect neighboring atoms. So here are the examples of what that would look like. So nitrogen with nitrogen. So I'm talking about here are two nitrogen molecules and how they would interact. And normally in the air, they interact barely at all. They'd have very, very weak forces or no forces at all when they slam into each other. But if we have a liquid or a solid nitrogen, there's got to be a way that they're held together, and that's what we're talking about here. So nitrogen has 7 electrons per, so we're talking about 14 total electrons. And generally those 14 electrons are around each atom about the same. But at some point, there forms what is called an instantaneous dipole, where one side will have more electrons than the other. This induces electrons from another molecule. Remember, and what's happening here, these molecules are getting close together and they're slowing down. That's the way to get them into this liquid or solid state. So now I've got a positive charge here. That's going to attract some electrons, which makes a negative charge. And then that causes the other side to be a positive charge. And this force right here is called the dispersion force. What holds those two molecules together? That is called a dispersion force, the attraction of a partial positive on one and a partial negative on the other. If we're talking about a noble gas like neon, neon has 10 electrons. So we're talking about one of the sides of the neon, and I'm just picking the right side this time. You can pick either side. So this side of the atom has more of the 10 electrons, and this side of the atom has less, so partial positive, partial negative, which will cause neighboring atoms to do similar things. And then these dotted lines represent the dispersion or London force. Again, they're very weak, and in most room temperatures, most times dispersion forces are not even held together because they're so weak. They can easily be broken, but this explains how anything that's nonpolar could ever be a liquid or a solid. It's these forces that hold them together. As we move down, we have dipole-dipole forces. And a dipole-dipole force is between two polar molecules. So two nonpolar molecules or noble gases, always London dispersion. Dipole-dipole, two polar molecules, let's give you an example of HCl. So HCl with another HCl next to it. The Cl is more electronegative, so it has what's called a permanent dipole, or a partial negative and partial positive charge on it all the time. Because of that, these neighboring molecules would have this force. Again, that's the dipole-dipole force right there. They'd have a force between them. This is stronger because these charges are stronger. This would be a stronger force than the dispersion or London forces because of the size of the charge. The other charges are temporary dipoles and are not a very strong attraction whatsoever. But what would hold these two molecules together is called a dipole-dipole force. So there's two others we're going to talk about. First one is hydrogen bonding. So hydrogen bonding are very polar bonds, and it causes it to be a little bit stronger than dipole-dipole. They're still between polar molecules, so I don't have that on here, but it's between polar molecules. And what makes it a stronger than dipole-dipole is because the large electronegativity difference. So there's only 3 atoms that would do this with hydrogen. Those are the phone atoms, fluorine, oxygen, and nitrogen. And the fact that they're smaller. Because some people would like, well, chlorine has a very similar or the same electronegativity as nitrogen. Or actually, I think it's nitrogen and oxygen are about the same. But chlorine's big. So it can't get as close to the hydrogen, and the size of the charge or the force is not as strong. So an example of this would be like water molecules attached to each other. So oxygen's more electronegative, so it's a partial negative charge. Hydrogen's less electronegative. Now we have another water molecule next to that, which will have the same charges, but this attraction from positive to negative of one molecule to the other is what's called a hydrogen bond. Essentially, it's a force, but unfortunately, it's called a hydrogen bond. So how is that different than the last one? Well, hydrogen was with chlorine. Here, if hydrogen is with any of these 3 atoms, it's considered hydrogen bonding, but it has to be those 3. So if the dots are drawn from hydrogen to one of those 3 atoms on another molecule, that is called hydrogen bonding. And these are stronger than dipole-dipole because of the electronegativity difference and the size of them. And then the last one is a dipole ion force. So if we imagine that sodium chloride is dissolved in water, sodium is a positively charged ion, chloride is a negatively charged ion. And what's going to happen is there's going to be a attraction between those ions and the water molecules, and that's what's going to keep them as ions rather than keeping them together as NaCl, because Na and Cl are attracted also. But what causes these guys to break apart is the attraction of the water molecules. So what's going to happen is these water molecules are going to arrange themselves so negative part of them is closest to that positive ion. And then again, we have this dotted line drawn as the force. That's not a very well done one, but that force right there. And I'll try and make it a little bit better here. But it's going to orient itself in space so the partially positive hydrogens here and this negatively charged ion have these ion dipole forces that hold together. And three-dimensionally, these waters would surround them all over three-dimensionally. Just showing it two-dimensionally a little bit how that attraction works. So this is the strongest of them all, and that's because of the size of the charge. Those positive and negative charges on the ions are large, even though the charge on the water molecules aren't bigger than the hydrogen bonding I just showed you, but these are a big charge, which causes this attraction to be even stronger than hydrogen bonds. So there are your four types of intermolecular forces that hold things together. This is what determines from molecule to molecule what type of melting point, boiling point, density. There's a lot of factors, viscosity, surface tension, a lot of factors or a lot of properties that are determined by the strengths of the forces between the molecules. And that is it.